Theo, I would like to explain why the point slope equation of a line works and how it was derived in class. So in module 1, we were given tables, something like this, or sometimes contexts where we would make the table. But remember, I would always make the table. And we would look for the pattern to describe this. And we learned how to write it both recursively and with an explicit equation. So if I want to write this as an explicit equation, a method that I can use to do this, not the only method, but a method is to sort of make an extended table that models the recursive pattern that we see. So most of you can see this pattern pretty easily. We start with 7, and every time we move down, we're adding 3. So in the extended table, you can say, well, the first term had to be given to us. We started with 7, and this one became 7 plus 3. And then the next line, we took 7 plus 3 plus 3 again. 7 plus 3 is 10, plus 3 more is 13. And this one became 7 plus 3 plus 3 plus 3. And then we practiced writing that with multiplication. So I'm going to start on the second one and we'll work our way back up to the first one. This is 7 plus 3 times 1. This third term is 7 plus 3 times 2, and this one is 7 plus 3 times 3. So if I wanted to back up to the first one, I could think about that as 7, or I could think about it as 7 plus 0 threes, or 3 times 0. So what we worked on when we practiced writing the explicit function was for some input in the future, n, f of n, the output, would have to follow this same pattern. So it would definitely have a 7 in it. And to that 7, we would be adding a whole bunch of 3s. And the question is, how many 3s do we have to add? So we practiced looking at how does this input of 4 relate to the number of 3s that we have to add? Or we could ask it as, how does this input of 3 relate to the number of 3s that we added on that term? Because in every case we see this is what's changing as we move down the y column of our table. And so most of you will see pretty easily that it's always 1 less 3 than whatever my input is. And so you called that n minus 1. So we create this explicit equation, f of n equals 7 plus 3 times n minus 1. That is one way to do it. And you'll notice what happens if you clean this thing up and distribute your 3, you would get 7 plus 3n minus 3, which equals, combining the 7 and the negative 3, 3n plus 4. So another way you could write it is f of n equals 3n plus 4. And for those of you who were my 0th termers who thought, well, I don't want to go through all the work of making this table, I just want to think about what would a hypothetical 0th term be if there was a 0th term in my table? You would have said, well, if I'm adding 3 moving down the table, I would subtract 3 moving up the table. So I have this hypothetical 0th term of 4, which shows up right here. So that is one way to make extended table and get your explicit function for a linear equation. Then later on in the homework, they gave us harder problems, and this was in the Go section of one of the homework assignments, where they would give you table, and they would maybe start with the third term, something like this. And they would have a pattern that was growing by a constant rate of change or had a nice common difference. So I'll come up with an easy one. What if we did 6, 8, 10, 12? Most of you can see pretty easily this thing is growing by adding 2 every time. So the constant difference is 2, and the slope is also 2 because this column is growing by adding 1 every time. Plus 1. So for people who use extended table, you would think about the recursive pattern is I start with 6, I add 2 every time I move down the y column of the table. So you would think I start with 6, the next term is 6 plus 2, the term after that is 6 plus 2 plus 2, the term after that is 6 plus 2 plus 2 plus 2. And we could shorten that up and think, well, this is 6 plus 2 times 0. I'm not adding any 2's to it. This is 6 plus 2 times 1. I'm adding 1 2 to 6. This is 6 plus 2 times 2. I'm adding 2 2's to 6. And this is 6 plus 2 times 3. So then we still have this same issue. What we really need to think about is how does this value, which is the thing that's changing in our extended table, relate to this input? Because those are the things that are changing. As the input changes, the number of 2's changes. So I want to relate this 3 to this 6. Similarly, I want to relate this 2 to this 5. And so most of you could see that pattern pretty easily. If the input was n, f of n, or the output, was going to equal a 6 plus a whole bunch of 2's. And the number of 2's I need is always 3 less than the input. So you would have called it f of n equals 6 plus 2 times n minus 3. Well, that's really the same as saying y equals 6 plus 2 times n minus 3. And because we're just adding these and addition is commutative, I can change the order of these things. Y equals 2 times n minus 3 plus 6. Well, here's what I want you to notice. 2, this 2, is the slope or the rate of change. So we know 2 equals m. And then the point that we knew was on the line that we used is this point right here, 3 comma 6. And notice where those values show up. Here's the 3 and here's the 6. And if we did this enough times, you would see that the pattern is always, let's write that point down, 3 comma 6 was the point that we knew was on the line. And if we did that enough times, you would be able to see the fundamental truth is that we've created this equation, m times x minus the x coordinate plus the y coordinate. And that is what we're calling the point slope equation of the line.